In this video, we will discuss the problem cousins of a given node. The problem says that we have been given a binary tree and a node, and we have to print all the cousins of the given node in the order of their appearance. And note that we should not print the siblings. So let us understand this with the help of an example. Suppose we have been given a tree like 1, then it is connected to 2, then 3, 4, 5, 6 and 7. Suppose we have been given this particular binary tree. So in this case, suppose we have been given the node x is equal to, let's say, 5. So what we have to do is we have to print all the cousins of the node 5. So if we see the node 5, so 2 is the parent of node 5, correct? 2 is the parent. And then we see that if 2 is the parent, then that means that 4 is the sibling. So if 4 is the sibling, so I will not print it. And if I observe here, so if 2 is the parent, then 3 is the uncle. And if 3 is the uncle, then the children of 3, that is nothing but 6 and 7 are the cousins. So we'll print 6 and 7 in the order of their appearances. Okay. So let's talk about another case. Suppose instead of this, what we had was, suppose we were given like the tree was given something like this. So in this case, if we observe, suppose we had been given the node as 7. So if the node was given as 7, so in that case, what are the siblings? So the siblings is nothing but 5 and 4. That is 4 and 5 you can write in this order. 5 will not, 6 will not be there because 6 is actually the 6 is actually a sibling. So the cousins are nothing but 4 and 5 here. Okay. Now let us discuss about a case when suppose 3 was given. So if we were given 3, so we can observe that for 3 there is no cousin actually, because for 3 you have what? You have 2 which is given as the sibling, and 1 is the parent, and there is no cousin. So when there is no cousin, then you can simply return the empty answer, I think. Okay. So these are the cases that we need to consider. Now when we talk about this, so how can we check? So suppose we have been given this node 6, right, as it has been given in the example. So what we can basically do here is we can say that we will be running a BFS call here. Like if we will observe now, so the cousins are always lying on the same level. We can observe this thing that cousins are lying on the same level, and which traversal will help us to iterate through the nodes on the same level. It will be nothing but a breadth first search. Okay. So when we are doing a breadth first search, so suppose the node has been given to us as x is equal to 5. So x is equal to 5. So we have to find all the cousins of x is equal to 5. So how can we do this thing? So for doing this, what we can basically say is that we will initially be running a BFS call, and we'll first of all insert 1. Okay. Then we'll find, after inserting 1, what we will do is we'll iterate until the queue is empty, and at every step for every level we will iterate independently. Okay. So we'll take out the size, and that much number of times we'll iterate. So first of all, the size is 1. So that means on the initial level there is just one node. So we'll take it out of the given tree, and when we take it out, so we are currently at this node 1. So with this, with respect to this node, we will check that does it have a left child or a right child that is equal to x. No, it does not have. So I'll say that okay, we can simply insert 2 and 3. So we'll insert 2 and 3 inside the stack, inside the queue, right? This will be a queue data structure that we'll be using, and then the size becomes 0. After this, we will reevaluate the size, and the new size of the queue will be nothing but 2 instead of 0. So 2 shows us that there are 2 number of nodes at the current level. Okay. Now we will check. So we will take out the front node. So the front will be 2. So I'll take out 2. The moment I have taken out the node 2, so we can say that 2 is like, does 2 have a left or a right child which is equal to, does 2 have a right child or a left child? Any child which is equal to the given node x? Yes. 2 has a left child which is equal to x, which is x is equal to 5. So we can say that we have found out that node which was there, which is having the child as 5. And now what we need to do is we need to observe this, that will we insert 4 inside our queue? No, we will not insert 4 inside our queue, because we want all the, like for a particular parent, for a particular current node, if it is having the left or the right child as the given node, then we will not insert the children of that particular node. And instead of that, we'll pop, like we will continue, we'll keep on continuing. Then what happens? The size reduces to 1. After that, what happens? We have this node 3. So when we have this node 3, so does it lie on the same level? Yes, definitely. So we'll have 3. So for 3 we can say that what we will insert is, we have not inserted 4 and 5, you can notice. Now what we will do is, we will say that 6 is the child. Okay, so we'll insert 6 and we'll insert 7. So left and right child both are existing, we have inserted them. Then we'll pop out 3 from the stack. Okay, and while we have done this, so we'll mark our flag as 1, and the moment a flag is 1, then we'll break, and whatever is present inside a queue, we will simply print it. So we have 6 and 7. Okay, so we'll basically print 6 and 7, and when we print the nodes 6 and 7, so they are nothing but our cousins that are present. Because if for the current level, if I was at currently at 2, then I'll not insert its children. Okay, because I'll not insert x, and I'll not insert the sibling as well. Then whatever nodes are present at that particular level, I'll insert all of their children, right, one by one, and then we'll simply break and print those children. That is the concept behind this particular question. Now let us try and write the code for it and see what happens. So what we will be doing here is, we'll first of all be given the root of the binary tree. So if it happens that the root is equal to null, okay, so in that case what we'll do is, we'll simply return the empty vector. Okay, otherwise what we would do is, we would first of all declare a vector that will store the answer. So we'll say that vector int answer, and we'll also declare a queue, right, queue of node star queue. Apart from this, we'll also have this thing that is inside a queue. First of all, we'll insert the root node. Okay, that is another thing that we'll be doing, and we'll have a flag initially marked as 0, initially saying that we haven't seen the node x up till now. For a particular current node, we haven't seen the node x up till now. Okay, that is what we will do, and then we will iterate until the queue is empty. So while the queue dot size is greater than 0, till that point we will keep on iterating, and what we will do is, we'll first of all find the size of the number of nodes at the current level. So the number of nodes at the current level will be nothing but q dot size. We'll take out the size of the node, we will take out the size of the queue, and then we'll iterate for the current level. Okay, and what we will do here is, we will say that node will take out the current node out of the queue from the front. So when we take out the front node, then we'll simply pop it out, just applying a normal BFS call, level order traversal. Then we will check that, suppose if the current left child is equal to x, or the current node right child is equal to x. So in that case what we will say is, we'll simply say that we'll mark the flag as 1. Okay, we'll simply say that we'll mark the flag as 1, and we can continue from here. Otherwise, what happens otherwise? So if the current node's left child is not equal to x, or the current node's right child is not equal to x, so in that case I will be inserting those nodes inside the queue. So I'll check that if the current node's left child is not equal to null, then I will do what? Inside my queue, I'll simply push the left child first of all. Then what I will do is, similarly, if the current right child is not equal to null, then we'll do what? We'll simply push the current right child. Okay, once we are done with this part, so what we would do is, after we have done the traversal for the current level, so if suppose if as I discussed, suppose if it is happening that at the current level we have found the parent of the node x. Okay, so in that case what we'll do is, we'll simply mark our flag as 1, and for all the for the uncle, right, for when the current node is an uncle, then we'll insert all the nodes of all the children of the uncle node. Okay, in this way we will be able to store the siblings, and when we have traversed for the current level, so we will check if the flag is equal 1. So that means that we have found out, we have stored all the children of the uncle node, that is all the cousins we have stored inside the queue. And then when we come out, so we can simply say that while the queue dot size is greater than 0, then if the queue is having some size, so we'll insert those elements one by one into the queue. So we'll say that answer dot pushback, nothing but the queue dot front dot data, we'll insert the data one by one, and then once we are done with this part, so we'll simply pop out the current node from the queue one by one until the queue is empty, and then we can simply return our answer here. Let us try and compile this code. So it seems to work on the samples. Let us submit this as well. Okay, it gives me a wrong answer here. Is there any case that I'm missing here? Its correct output is -1. Okay, so if the answer is not existing, then I think I need to print -1 if the answer is not existing, right? So after this part, like suppose I have stored right inside my vector, so I need to check as well, like if my answer dot size is equal to 0, in that case I'll simply return a vector that will store -1. Else what I will do is, else if there is no cousin, then I'll simply print -1. Otherwise I'll print the answer vector that is storing the cousins. And similarly I need to do it here, that if the root is null, then I need to simply print -1. Let us now try and compile it. It works on the samples. Let us quickly submit this code as well. So you can see that our code was able to pass all the test cases. And now talking about the time complexity of this code. So the time complexity of this code will be nothing but order of n, and the space complexity will also be order of n, because we are using a queue for storing the nodes, and the time complexity is order of n because we are doing a BFS traversal on this particular given tree. Thank you. In this video, we will discuss the problem count the number of subtrees having the given sum. So the problem says that we'll be given a binary tree and will be given an integer x, and our task is to find the number of subtrees that are having the same sum as x. Okay, so let us quickly discuss this test case that has been given to us to understand better. Suppose we have been given this particular test case and we have been given the x value as 7. So let us quickly copy it. Let's say we have been given a test case like we have 5, then the child of 5 is -10, then another child is, let's say, 3, then 9, then 8, then we have -4, then we have 7. Okay, when we have this kind of a tree given, so what we have to do is we have to find all the subtrees. We have to find the count of all the subtrees that are having the value as 7. Okay, that are having the sum as 7. So what are subtrees basically? So if I talk about this particular node, so this particular node, if I talk about, so this particular node is the root of this subtree. Okay, similarly this particular node is the root of this subtree, and the original root of the tree is also a subtree. Suppose if I extend this like this, like it was -5, let's say it was 10. Okay, so this would be a subtree. Suppose if I had further extended it something like this, so this would also be a subtree. So basically a subtree is a part of a tree, and we have to find all the subtrees that are having the sum as x is equal to 7, right? So if we will observe, so what we can do here is, whenever you get trees problem, so we can apply recursion here. Very simple and short, we can apply recursion here. And what we can do is, we can apply recursion by observing some of the things. So if we observe here, so we can observe here that first of all we can apply recursion from the root of the tree, and we can go one by one down. Okay, then what will happen is, once we reach the leaf nodes, okay, once we reach the leaf nodes, then we can observe that we have this particular node that is having the value as 7. Okay, now talking about this, -4 is not equal to 7, and 8 and 9 are also not equal to 7. So up till now my count would be 1. Okay, then what will happen if I have to consider this subtree? Okay, so what will be the sum of this subtree? The sum of this subtree will be nothing but the sum of the left subtree plus the right subtree plus the current node. So that is nothing but 9 minus 10 plus 8, which is equal to 9 minus 10 plus 8, which is basically equal to 7. Okay, so I can see that this particular subtree that is there, it is having the sum as 7. So I'll count it as well. Okay, so my count changes to 2. So up till here the subtree value is 7, right? Then for this particular subtree, I'll first of all get some value from the left. So my left subtree returns what? My left subtree returns a -4. My right subtree returns a 7, and my value is what? 3. So left subtree plus the value of right subtree plus the current root value. So that will be nothing but 10 minus 4, that is 6. So this returns a 6. Okay, and this returns a 7. So if I talk about the subtree that is rooted at 5, okay, so in this case we can see that the left subtree is what? The left subtree is having sum as 6, right subtree is having sum as 7. So the value of the subtree that is rooted at 5 would be nothing but 7 plus 5 plus 6, and this is nothing but 18, which is not equal to 17. So I could find only two subtrees that are having the value, or that are having the sum as x is equal to 7. So I can find only two subtrees that are having the sum as 7. So we were able to observe that when we want to get the values of the subtree, when we want to get the sum of the subtree, So we can get the sum of the subtree by adding the left subtree of it plus the sum of the right subtree of it plus the current root value. And when we reach a particular node that is null, suppose we reach a particular node that is null, then we can simply return 0. Suppose I call for this node and it returns me let's say I call for this node 7. Okay, then I call for its left child, so it is null, so it will return a 0. If I call for the right child, so it is null, so it will also return a 0. Then the value of the subtree which is rooted at 7 would be nothing but the left subtree sum, which is 0, plus the right subtree sum plus the current root value, that is something but 7. So that the overall sum will be 7, and if it is equal to x, then I'll count it, otherwise I'll not count it and return the subtree sum to my parent. Okay, that is what we can try to do here. So let us quickly write the code for it and try to and understand this. So what will be given is, will be given the root of the original tree. So we can basically write a recursive function in which we can try to call. So what we will do here is, we will first of all say that we can have a counter which will be initially marked as 0. Then we can recursively call, and what we can pass here is, we can first of all pass the root value, then we can pass the x, apart from the x we can pass the count, which will get updated from this particular function. We'll update the count, and then after this recursive call is done, so the count will store the number of subtrees that are having the sum as x. Then what we can do is, we can have the recursive function here, because the recursive function will be returning int, because it will be returning the number, that's the sum value of a particular subtree rooted at that particular root. Okay, so what we will do is, we will first of all pass the root, so node star root. Okay, once we have passed the root, so we'll also pass the value x. Okay, and we'll also pass the ampersand count. We'll pass the count with call by reference, because we, whatever changes, whatever increments we do in the count, we want them to be reflected inside our main function as well. So if it happens that the root is equal to null, if the root that I'm at, if it is null, then that means I can simply return a 0. Otherwise what I'll do is, otherwise I'll get something from the left, I'll get some left sum. Left sum will be nothing but the sum of the left subtree. Okay, so if I want to get the left sum of the left subtree, then I'll call this recursive function with the root left. Okay, I'll go to the left child, and then this will work. Okay, so I'll pass the x and I'll pass the count as well. Okay, then similarly I want the right subtree. So the sum of the right subtree will be nothing but, I'll call this recursive function, I'll pass the root right, okay, because that will be the parent there, and I'll pass x and I'll also pass the count there. Okay, once we come back, what will the sum of the current subtree? So sum will be nothing but the left sum plus the right sum plus the current root value, so that will be nothing but the root data. Okay, and I will check that if this particular sum is equal to x, in that case we will do increment the count, and once we have incremented the count, so we will simply return this sum to the parent. Okay, that is what we will do. And you can observe easily here that when I call for my leaf node, suppose I'm standing at the leaf node, so when I call for its left child, then it will return me a 0. When I call it for its right child, so it will return me a 0, and then the sum would be nothing but 0 plus the root data. Suppose the root data was 7, so in that case, if the sum is equal to x, suppose x was 7, so in that case I'll simply count it and then return the answer. So this is how my count will get incremented one by one. Let us try and compile this code as well and see what happens. So you can see that we are getting the same output on the samples. Let us try and submit this code as well. So our solution was able to pass all the test cases, and this is how we do this problem using this concept. And talking about the space complexity and the time complexity of this code, so time complexity would be nothing but order of when, because we are iterating through each and every node of the tree exactly once, and the space complexity would be nothing but the recursive stack space, that will be nothing but the order of height of the tree. Okay, so in case if you understood this video, make sure to hit the like button. Thank you.